Okay, so today we're going to talk about kind of like a summary of curve sketching. So technically speaking, we're not learning anything new. We're just kind of putting our knowledge of analysis and calculus together to kind of get a sketch of a curve or a graph that's pretty much 100% accurate to what it would be if we were to use a graphing calculator. So basically, the comment I want to make here is that we have sketched some curves in previous sections. So we will now follow these steps to sketch a curve from this section on. So one comment I want to make here is that in the book or in your when you work on the problems, it's going to say follow the 7 steps to sketch this curve and so on. So it's kind of like the book is assuming you know the 7 steps. On the test, you don't have to memorize these 7 steps. So on the test, I'll tell you step by step what I want you to do. Okay, so of course, I care more about you being able to use the first derivative to find intervals of increase and decrease and so on. I will not say, oh, memorize these 7 steps. So what I'm going to do today is I'll give you the 7 steps. We won't really do an example because we've done so much of this. When you work on the problems, you'll also get some experience with this as well. So I'm just going to give you kind of like the 7 steps that we need to follow. So the first step is strictly to find the domain. Okay. Now, why is it important to find the domain? Reason being is this: we want to find the domain of the curve. Now, what's going to happen is that this gives us an idea of the restrictions of the curve. So in other words, we're going to basically notice, hey, if 2 is not in my domain, well, when I'm trying to figure out certain intervals, I don't need to include 2 in there because something's going on at 2, whether it's a vertical asymptote or whatever it may be. Okay, so the second step is finding intercepts. So you want to find y-intercepts and there's only going to be one by setting x equal to 0, and then you want to find x-intercepts. By setting y equal to 0. Okay. Now, as far as finding the x-intercepts go, sometimes finding x-intercepts may be difficult, so we may omit it. But usually we want to find x-intercepts. So we'll make a comment here. We may omit finding x-intercepts if we have a complex or complicated equation to solve. Okay, so for the most part, you should be able to find your x-intercepts. Okay, so keep that in mind. It's not that we're going to be ignoring it, but from time to time, it may be difficult to find. So we might just say, you know, let's skip finding the x-intercepts. We could still sketch a pretty decent graph. Okay, but for the most part, you'll be able to find the x-intercepts. So the third step, we want to determine symmetry of a function. And if you remember, earlier on in the year, we did graph absolute value functions where we checked for symmetry, because symmetry helps us kind of cut our work in half. So basically, what are the tests of symmetry? If we say if f of negative x equals to f of x for all x in our domain, so our D is just the domain, so this means what? Then f is an even function, and if it's even, what is it that we know? You probably already know this. F is symmetric with respect to, remember WRT means with respect to, so with respect to the y axis. Okay, and then we could also say if f of negative x equals to negative f of x for all x in our domain, then we could say f is an odd function. Then f is an odd function and f is symmetric with respect to the origin. Okay. And then, of course, we also have functions that are periodic. And so for periodic functions, usually these are the trig functions that we kind of expect to be periodic. So if I could kind of graph one period, then I can force out infinitely many periods. So here's another comment we can make is if f of x plus p equals to f of x for all x in our domain, where p is a positive number, then f is called a periodic function. And the smallest number, p, is called its period. So like I said, for the most part, we will have kind of, as far as periodic functions go, we will have trig functions that we'll see that usually have these periodic characteristics, okay? So if you think about it, the first three steps so far have been strictly knowledge from math analysis or pre-calculus, okay? So moving on to the fourth step. So the fourth step is simply finding the asymptotes. And we know that usually asymptotes arise with rational functions, but we have other functions that have horizontal asymptotes that aren't necessarily rational functions, but most of these asymptotes come about from rational functions. So we want to look for horizontal asymptotes. And if you remember, we actually did find horizontal asymptotes in this class earlier on in the year. So here's what we know. If the limit as x approaches infinity of f of x equals to L, or the limit as x approaches negative infinity of f of x equals to L, what is it that we know? We can say that then the line y equals to L is a horizontal asymptote So what we know is then, the other statement we could say is the following. If the limit as x approaches infinity of f of x equals to plus or minus infinity, one or the other, then what do we know? We get no horizontal asymptote. But what's important about this? If we see this, then we have an idea. So, but we get an idea about its end behavior. So basically what we're saying is, as x goes to infinity, if f of x goes to infinity, then what do I know? As x gets larger, my function goes up forever. Or if it's negative infinity, then it goes down forever. So it kind of gives us an idea as to what the end behavior looks like. Okay. Now, the second step is vertical asymptotes. So what we know is as follows. A vertical asymptote is described as one of the following. So what we could say is that, here's the first condition. The limit as x approaches a from the right side of f of x, what happens? You go to infinity. Or you could go to negative infinity. It doesn't matter, right? So what does this mean? As I approach a from the right side, my function goes up to infinity or down to negative infinity. So that's one possibility. Or what do I know? If I approach a from the left side, my function goes to some sort of infinity. So it could be infinity or negative infinity, plus or minus infinity, one or the other. Okay, so that's what happens. So vertical asymptotes come about when you approach a fixed number. Your function either goes up to infinity or negative infinity. Same thing here. If you approach a from the left side, your function either goes up to infinity or negative infinity. So that's kind of like what's going on here. Okay, so if you remember, I mean, for rational functions, what is it that we learned? We can say, recall that for rational functions, the zeros of the denominator are practically our vertical asymptote. The zeros of the denominator are vertical asymptotes. Okay, now, the last type of asymptotes that we discovered from analysis are called the slant asymptotes. So slant asymptote. So slant asymptotes means you have like this slanted line, and in the long run, your function approaches that slant asymptote. So describing this in terms of calculus, here's what this says. If the limit as x goes to infinity, so what does that mean? As x gets larger and larger and larger, or it could also go to negative infinity. Here's what we know. Your function minus this line. See, this is a slanted line. So what do you notice? If my function approaches this line in the long run, then what should the difference between these approach? It should approach to 0. Because think of it this way. If I have a slant asymptote, okay, here's my function, mx plus b. Okay, that's the equation. If you look at this, this is my line, slant asymptote, and here's f of x. What do you notice? As x gets larger and larger, what's the difference between f of x and this line? It gets smaller and smaller, and that's what we mean. As x approaches infinity, if this is truly a slant asymptote, then the difference between these two should approach 0, because as f of x gets really close to this line, then their difference should be very, very close to 0. Okay, so that's kind of like expressing this in terms of calculus. So we could say then the line y equals to mx plus b is called a slant asymptote. Now, in analysis or in pre-calculus, what do we learn? For rational functions, slant asymptotes occur when the degree of the denominator is one more the degree of the denominator is one less than the degree of the numerator. So if you remember, when you look at your rational function, if the degree of the denominator is one less than the degree of the numerator, then we know that we are going to have a slant asymptote. And basically, and this is found by applying long division. Okay, so if you remember, just to kind of summarize what we did in analysis, we said, look, if you have a rational function, if the degree of the denominator is bigger than the degree of the numerator, then we always have a horizontal asymptote at y equals 0. And then we said if the degree of the numerator and denominator are the same, we have a horizontal asymptote at somewhere other than 0. But it's still a horizontal, like it could be at y equals 1 or 2, and that depends on the coefficients. And then if the degree of the denominator is 1 less than the degree of the numerator, then that's where my slant asymptote comes from. Okay, and then you could find it by using long division. So if you need to refresh your memory on this fact, we can talk about it in class. Just make sure to ask me about it. Okay, now steps 5, 6, and 7 is where calculus kicks in. So if you think about it, steps 1 through 4 have been everything we've done in analysis. Okay, now as far as step 5 goes, here's where calculus kicks in. So the next step is we want to find intervals of increase and decrease. So how do we do this? We find f prime of x, and then we make a sign chart. When f prime of x is greater than 0, that means f is increasing. And then we could also say when f prime of x is less than 0, that means f is decreasing. Okay, so that's step 5. And then step 6 is to find the local maxes and min values. So local max min values. So once we find our local maxes and mins, we would say find local maximum or minimum by using first derivative test. And the reason why we want to use the first derivative test is kind of like, because in step 5, if we're going to spend our time finding the intervals of increase or decrease, then we could use step 6, kind of goes with step 5 right away. So basically, how do we use the first derivative test? Just to kind of summarize this, which, by the way, this is pretty much done in step 5. You find critical numbers C, and remember our critical numbers are when f prime of C equals to 0 or does not exist, okay? And then the second thing you do is you check if f prime changes from positive to negative at C, then what do we have? Max value of f of C. Okay, then we could say if f prime changes from negative to positive at C, then we have what? A local minimum value at f of C. Okay, and maybe here we should also add local, okay, because these are how local maxes and mins are found. Okay, but like I said, step 6 we kind of get for free out of step 5, so it's not that you have to do step 6 start all over again. Since you've done step 5, just look at your critical numbers. Does it change from positive to negative or negative to positive? If it does, then we have a local max or a local min. Okay, so the last step, which I'm sure you can guess, because after intervals of increase and decrease, what we've always done is we found intervals of concavity. So we would want find concavity and points of inflection. So finally, what we would say is find f double prime of x, and once we find f double prime, then what do we want to find? We want to find all the real numbers where f double prime equals to 0. So we're going to say and find all real numbers such that f double prime of C equals to 0. And then remember, we make a sign chart for this. And then we could see if we have inflection points or not. If f double prime of C is greater than 0, then f is concave up. If f double prime of C is less than 0, or not C, let's call these x's, sorry, not C, then f is concave down. And then how do I find my inflection points? The inflection points is when, if C is 0, what does that mean? And by the way, I hope you guys could see why this shouldn't be f prime of C, because f double prime of C, because we said f double prime of C is 0. So what we know is if the second derivative is positive, f is concave up. If the second derivative is negative, then f is concave down. And then the third step, the third thing we could say is this: if f double prime of x changes from plus to minus or minus to plus, we don't care if it's positive to negative or negative to positive. So if it changes from positive to negative or negative to positive at C, then what do we know? Then we have an inflection point at x equals to C. Okay, so then the inflection point will be what? C comma f of C. That's how you'd find it. Now remember, you plug it into the original function. So once you gather all these information, once you know your intervals of increase, decrease, intervals of concavity, then step 8 is kind of like sketch the graph using steps 1 through 7. So just really quickly to summarize this, the first 4 steps, which is finding the domain, x-intercepts, symmetry if there are any, and of course horizontal vertical asymptotes if there are any, that's all from analysis. After that, steps 5, 6, and 7 is basically everything we've done in this chapter. So there's nothing really new in this section. All this section is doing is saying, look, let's grab everything we learned in the past, let's grab everything we learned in calculus, let's put it together to get a really nice graph of what it is we're trying to do here, okay, or the function that we're working with. So that's where I'm going to stop. I'm not going to do an example because I feel like we've done plenty of these types of problems. So we'll just work on problems from the book in class, and if any questions arise, then we'll go over them together as a class. Okay, so that basically takes care of section 5, which, like I said, we didn't learn anything new. Okay, so that's basically it.